Hi, this is Ramachandra, a fifth-year PhD student at North Carolina State University. In this talk, I'm going to introduce our paper called UDF-to-SQL Translation through Compositional Lazy Inductive Synthesis. Other authors of this paper are Yuanchao Xu and Xipeng Shen from North Carolina State University and Isha Didik from the University of Texas at Austin. In this paper, we propose a novel program synthesis technique called compositional lazy inductive synthesis to translate user-defined functions into SQL. Many data processing systems allow SQL queries calling user-defined functions, or UDFs. For instance, in Spark, we can first define a function using the Scala language. This example function converts the Celsius degree to Fahrenheit degree. And then we can register the function into the query engine with a name. Then in a SQL query, we can use the registered name to call the function. Other systems define and use UDFs in similar ways. UDF offers flexibility to users, but with the cost of performance. This is because UDFs usually involve cross-language type conversions, and their implementations may not be so efficient as SQL built-in functions, which are usually highly optimized. Most importantly, UDFs are largely black boxes to the query optimizer. This makes it hard to optimize UDFs in queries. One way to optimize UDFs in queries is translating UDF to SQL. This is possible because many UDFs can be rewritten using SQL built-in operators or functions. For example, this UDF seen in the previous slide can actually be rewritten using SQL built-in operators. So the query with the UDF becomes a pure SQL before feeding into the query engine. A previous work called Freud takes this path to optimize UDFs in queries. It is a rule-based method, which means the UDF-to-SQL translator relies on a set of predefined rules to do the translation. In general, such a method is hard to handle loops. For instance, this function contains a loop to detect if a string is a palindrome. In SQL, the same task can be done by checking if the string equals to its reversal. But it is hard to come up with a general rule to perform the translation. To address this problem, we propose compositional lazy inductive synthesis, abbreviated as CEGIS. It is a program synthesis technique that finds a target program by search. Generally speaking, program synthesis techniques have scalability issues because the size of search space is exponential to the size of target program. In this work, we leverage program composability to address the scalability issue. At a high level, CEGIS works as this figure shows. Given a query with the UDF, it first constructs a data flow graph for the UDF. And then, based on the UDF, it decomposes the UDF to small code pieces, which can be considered as subqueries. For each code piece, we use counterexample-guided inductive synthesis, also known as CEGIS, to find an equivalent SQL piece. If the synthesis fails for some code pieces, the synthesizer tries another decomposition. If all code pieces of the decomposition are translated to equivalent SQL, the SQL pieces can be recomposed, and then we can use the recomposed SQL to rewrite the UDF in the query. Finally, we get a pure SQL statement. I will use a running example to explain our method in detail. The left side shows the query with the UDF. The UDF named toTitle capitalizes the initial letters of all words in its first argument, the string S, and converts all other letters to lowercase. If the second argument T is true, it also trims the string S. The right side is an equivalent pure SQL query. I will show how our method translates the query with UDF on the left side to the pure SQL on the right side. The first step is to construct a DFG of the UDF. Let's see what the DFG would look like for the running example. The DFG starts from the function arguments and then the node for the first branch of the if statement at line 2. Its value is assigned to a temporary variable called TS, and then the node performing branch selection. Then the node for line 3. And here we put the two statements into a single node because the statement at line 4 is simply a constant value assignment. Finally, it's the node for the return value. After obtaining the data flow graph, we use counterexample-guided inductive synthesis, abbreviated as CEGIS, to find an equivalent SQL expression for each DFG node. CEGIS is a common pattern of program synthesis. And this figure shows our instantiation of CEGIS. Given a source code piece in the UDF, we first randomly generate some input-output examples of the code piece. Then we use a program by example synthesizer to find a candidate in SQL that satisfies the input-output examples. We further use a verifier to check if the SQL candidate is equivalent to the source program. If not, the synthesizer gives a counterexample proving the inequivalence. The counterexample is used to augment the example set. Then there goes another synthesis verification iteration until we find a target SQL program equivalent to the source program. Let's see an example of CEGIS. Suppose we have a source program checking if a string is a palindrome. And the initially generated input-output examples are like this. It says that a string A is a palindrome and string XY is not. In the first iteration, the program by example synthesizer may find a candidate program like this. This program satisfies the given examples, but the verifier will figure out that this is an invalid candidate and give a counterexample. Let's say B. Because the source program returns true for string B, but the candidate returns false. The counterexample is then added to the example set. Then in the second iteration, the synthesizer may output a candidate program like this. It is still invalid, and the string ABA is a counterexample. Again, the counterexample is added into the example set. Finally, in the third iteration, this candidate may be found. It is equivalent to the source program, so it is the target program. Let's go back to our running example. We already have a data flow graph. The next step is to find an equivalent SQL expression for each node using CEGIS. For this node, the equivalent SQL is trim S, and this node can be translated into the if function in SQL. This is equivalent to null S, to null S1 in SQL. So far, so good. But for this node, there is no equivalent SQL expression, so the synthesizer fails. In such a case, we try another decomposition by merging the failed node with its adjacent node. The CEGIS synthesizer can find an equivalent SQL for this merged node, which is init cap S1. Now, all the nodes in the UDF DFG are translated into SQL, so we have a SQL DFG. We can recompose it back to a SQL expression and then plug it into the query with UDF. Finally, we get a pure SQL. In summary, the complete algorithm is like this. Given a query with the UDF, it first decomposes the UDF into a DFG. Then for each node in the DFG, it uses the CEGIS synthesizer to find an equivalent SQL expression. If it fails for one or more DFG nodes, it coarses the decomposition by merging the failed node with its adjacent node. The loop continues until all nodes in the DFG can be translated to SQL. Then it recomposes the SQL DFG to a SQL expression, which is equivalent to the UDF. And finally, it plugs the composed SQL into the original query with the UDF to get a pure SQL statement. It is worth noting that the node-wide CEGIS is actually embarrassingly parallel because each node in the DFG can be translated separately. I have shown how our method works. The following slides will show how it performs. To evaluate CEGIS, namely compositional lazy inductive synthesis, we randomly selected 100 Spark UDFs from GitHub. We use Spark as our test bed because UDFs are extensively used in Spark. After manual inspection, we found 63 of the 100 UDFs have SQL equivalents, and 52 of the 63 UDFs contain loops. We found that CEGIS can synthesize target SQL for 58 of the 63 convertible UDFs with a 1 hour timeout threshold, and 54 of them are solved within 5 minutes. 46 of them are solved in less than 1 minute. In fact, the median synthesis time is just 9 seconds. Among the 58 solved UDFs, we found that 56 of the synthesized SQLs are more efficient than the UDF counterparts. The speed up factors range from 1.3 to 16.3 with a geometric mean of 3.5. Only 2 synthesized SQL expressions are slightly slower than the original UDFs. This table compares CEGIS against some closely related works. Freud is a syntax-driven method and handles no loops. So it can only translate at most the 11 loop-free UDFs. UDF decorrelation and deep range are syntax-driven methods as well. They deal with a special kind of loops called cursor loops, which iterate through results queries. But Spark does not allow cursor loops in UDF. So they also can only solve those loop-free UDF benchmarks. QBS and Casper are 2 program synthesis techniques performing source-to-source code translations. Casper is more advanced, and we consider it as the state of art. Although its public available tool is not designed for UDF-to-SQL translation, we re-implemented its method for our domain. And we found that Casper can only solve 21 UDFs within a timeout threshold of 1 hour. Finally, we did an ablation study to see the importance of the features of CEGIS. We ran CEGIS in parallel with 4 CPU cores and in serial with only 1 CPU. We also ran CEGIS without the DFG decomposition, which means the CEGIS synthesizer tries to directly find the equivalent SQL expressions of the UDFs. This figure shows the results. The x-axis is the UDF IDs ordered by the synthesis time, and the y-axis is the cumulative synthesis time. We can see that the parallel CEGIS is much faster than the serial CEGIS. And without the decomposition, it becomes much less scalable. That is all for the talk. Thank you.